Solving differential equations in terms of x. So here we'll be looking at solving differential equations that look something like this, where we have a derivative and it equals some function of x. And these can be relatively simple to solve because we can imagine timesing both sides by dx, where these dx's will cancel out and we'll have dy equals f of x dx, and then we could integrate both sides with little problem. So let's have a look at an example. So solving the differential equation dy dx equals 3x squared, given that when x equals 2, y equals 11. So let's just move our dx to the other side. So we get dy equals 3x squared dx and integrate both sides. Integral of 1 dy is y, and the integral of 3x squared, we just add 1 to the power, divide by that power, plus a constant, and those 3's will cancel out. And we get y equals x cubed plus c. And this time we'll give an initial conditions, so we can sub those in. When y equals 11, x equals 2, so we get 11 equals 2 cubed plus c. So 11 equals 8 plus c. So minusing 8 from both sides, we get c is equal to 3. So therefore, y equals x cubed plus 3 is the solution to that differential equation. Let's have a look at another example. So the first part of the example is to show the d dx of x plus x inverse tan x minus a half ln of x squared plus 1 all equals inverse tan of x plus 1. So this just means we need to differentiate all of this and show that it equals this. So differentiating x just gives us 1. Now differentiating x tan inverse x, we'll need the product rule. So that's just going to be the derivative of our first term, which is 1, times our second term, which is inverse tan of x, plus the derivative of our second term, derivative of inverse tan x, is 1 over 1 plus x squared, times our first term, which is x. Now, deriving this log function, we can just leave the minus a half out the front, and the derivative of a log function is just the function inside goes into the denominator, and the derivative of that function goes into the numerator. So derivative of x squared is 2x, and derivative of 1 is 0. So we end up with this for our derivative. Let's simplify it. So we just get 1 plus 1 times inverse tan is just inverse tan x, plus, well, x times 1 on x squared is just x over 1 plus x squared. Here the 2 and the 2 will cancel, so we get minus x over x squared plus 1, and now x over 1 plus x squared minus x over x squared plus 1 cancel out, and we just get 1 plus the inverse tan x, which is exactly what we wanted on the right hand side. Okay, let's look at a second part to the question. As we want to find the solution to the differential equation, dy dx equals inverse tan x plus 1, and we know that y of 0 is equal to 0. So what we want to do is multiply both sides by dx. So they cancel out, and we just get dy equals the inverse tan of x plus 1 dx. And now we can integrate both sides. So we just get y equals the integral of this, we can use part A, because if the derivative of this equals this, the integral of this must equal this. So we end up with x plus x times the inverse tan of x minus a half ln of x squared plus 1 plus a constant. And we had the initial condition that when x is equal to 0, that y equals 0. So let's sub that in. So we have 0 equals 0 plus 0 times inverse tan of 0 minus a half times ln of 0 squared plus 1 plus a constant. So we just get 0 equals, well, that's 0. 0 times this is 0. Then we get minus a half of ln 0 squared is 0 plus 1 is 1. And ln of 1 is 0. So we just get c equals 0. So the solution to the differential equation becomes y equals x plus x tan inverse x minus a half ln of x squared plus 1 as the solution to the differential equation. Okay, let's have a look at another example. This time we're going to look at a second order differential equation. It's going to be d2y over dx squared equals a half outside of e to the x minus e to the minus x. And we're given some initial conditions that y of 1 equals 0 and y dash of 0 equals 1. So here we want to integrate both sides with respect to x. So integrating this side with respect to x and integrating this side with respect to x. So integrating our second derivative is going to give us our first derivative. So we get an expression for dy dx. The half we can take outside the integral. And then we get the integral of e to the x is just e to the x. Now, the integral of e to the minus x, we divide by the negative, so we're going to get a positive, and we get e to the minus x. And we're going to get plus a constant. And we were given an initial condition on the first derivative saying when x equals 1, the first derivative, when x equals 0, the first derivative equals 1. And another way to put this is that when x equals 0, dy dx equals 1. So let's go ahead and sub that in. So we get 1 equals a half times e to the 0 plus e to the minus 0 plus a constant. So we get 1 equals a half outside of 1 plus 1 plus a constant. So we get 1 equals a half times 2, which is 1 plus the constant, and minusing 1 from both sides, we get the constant equaling 0. So that gives us our final expression for the first derivative, where dy dx equals a half outside of e to the x plus e to the minus x. Now we still haven't solved it because we need to find an expression for y, but we're going to go ahead and integrate both sides again with respect to x. So the integral of just dy is going to give us y. The half we can throw outside the integral. Then the integral of e to the x is e to the x. The integral of e to the minus x will divide by the negative, so we get it back to a negative, e to the minus x plus a constant. And we're also given the initial condition at the beginning when x is equal to 1, y is equal to 0. So we can sub that in. So when x is equal to 1, y is equal to 0. we get a half outside of e to the 1 minus e to the minus 1 plus a constant. So this just means our constant. We can take out this term to the other side, so we get minus a half outside of e minus 1 on e. And then we can go ahead and sub that back into our equation for y. So we get y equals a half outside of e to the x minus e to the minus x minus our constant, which is a half minus a half outside of e minus 1 on e. And that's our final solution for that differential equation.